be here. I guess all of this is the Greater New York meeting. Buffalo's really only loosely the Greater New York meeting. But, I'm from New York City, so it's like coming home. So the topic on this talk, and I think this session, was kind of a shift from what we heard about earlier. But I think in the end, you'll see that a lot of the ideas transfer, and even with the demo that we're giving at lunchtime, taking the same exact ideas and applying them to video segmentation. Okay, so before I begin, I need to thank my colleagues Alan Newell, Adrian Sharon, Owen, Raja, and Dugu for their contributions to these slides. This is work that's been going on for about the last 5 years or so. And it's largely about finding and quantifying things in medical images, things being anatomies, pathologies, say brain tumor or hippocampi for schizophrenic research or Alzheimer's and so on, and work like lumbar discs and trauma, ultrasound trauma. The challenge here is that we not only need to segment the image, but we need to know what we're segmenting so that we can then tell the physician what's going on. Over a longitudinal study of brain tumor, has this patient progressed, has the tumor progressed, or has the tumor receded? This is quite challenging because we have to look at the images not only at a pixel scale, but at a multiple scale. But also, if you look at different structures in the image, like these lumbar discs in this T2 spur image, in appearance they look quite similar, both in terms of their intensity level, their rough shape, and we're only able to recognize and segment them if we look at them at a higher level. And so we are looking at layered models where we're taking pixels and then through objects and potentially even as high as scene level. And we'll talk about different ways of doing that for a couple different medical imaging problems. One of them being brain tumor, high-grade gliomas, which are examples on the top right up there. And the other are the lumbar discs. And I will not give you any, let's say, sophisticated or complicated, rigorous mathematical definition of layered models, but rather I'll give you a couple examples of how we've used them. So it's kind of like definition by example, and then talk about it a little bit at the end about how we're trying to moving towards a more formal definition of layered models and other ways in which we've used them. Okay, so in medical imaging, joint segmentation and recognition is quite important. As I mentioned, we need to quantify the anatomy and the pathology to aid clinical decision, surgical planning, and so on, provide data for treatment analysis, learn whether or not a drug is working, and it's quite challenging. Pathologies especially vary in appearance greatly. Their size, their shape is different from patient to patient. Inside of one patient, not only are they alone different, but they can deform nearby structures. On the right of the slide, you see some cartoons about high-grade gliomas. These are the most common and the most invasive brain tumors. This is what the late Senator Kennedy died from not many years ago, where you see that, so the top left example there, so this example here is early grade glioma, so it looks very enhancing. It's kind of a bright golf ball right in the middle of the brain. Why is it bright? Well, the cells of the tumor have broken the blood-brain barrier, and there's a lot of fluid in those cells in comparison to normal brain, so they're enhancing on the scan. However, the tumor grows so quickly that it kills itself, and so then you get dark in the middle of the tumor. Those are dead tumor cells with some enhancing rings. Then you have some variation on the outside, some debris, some vasculature, some veins and so on inside of the tumor. But also around the tumor you have edema, which if you're able to quantify the edema, which tends to follow white matter tracks, then you'll have a good sense of the prognostic condition of the patient. So apparently the more swelling, the faster it's growing. So we'd like to get a good sense in this particular application what's going on there. Okay, so the first of the two methods that I'm going to present is briefly called Bayesian SWA, or layered Bayesian segmentation by weighted aggregation. It builds on graph-based segmentation that I'm sure nearly everyone in the room has heard about. Okay, so the basic idea is you have pixels in the image. For every pixel, you define a node in the graph. You connect them to the nearest neighbors. 4 connected for a 2D image, 6 connected for a 3D medical image, which is what we're working with here. At every pixel, for every voxel, you have some statistics or features. Let's call them S sub B. These might be the multi-sequence intensity, so T1, T2, flare. At a higher level, if you're looking at a region, these might be texture parameters or so on. And we also want to define a class label, most C sub B. So this might be hidden. This is something like normal brain or tumor or edema, for example, brain tumor example. We want to infer those class labels at the image. Okay, that's our goal. Okay, very off-the-shelf thing to do with graph-based segmentation. Define some affinity function. So for every edge between the two nodes, you have a variable WUV, which is defined essentially as e to the minus some distance, usually some absolute or square distance or something like that. Basically, the more similar the features are to those two nodes, the higher the affinity. The less similar, the lower the affinity. Okay, regions are defined by cuts, like this yellow thing here. And say you have a region R in your image, you might define some saliency function, R, a gamma on R, right? So it's a ratio of the sum over all the affinities along the boundary of that region. So we want that sum to be really low, so we want it to be well separated from its surrounding, over the sum of all the affinities within the region. We want that to be high. We want to have some kind of a consistent affinity inside of that region. Okay, this is called normalized cut. This is not something new. Right, and so there are very well understood, well studied ways how we can do that at a pixel level. As I mentioned though in the first slide, doing things at a pixel level in medical images is oftentimes not good enough. Okay, so there's a hierarchical algebraic multi-grid approach to approximately solving the normalized cut method called segmentation by weighted aggregation, which was originally published, I think, by H. and Sharon and colleagues around CVPR 2000, 2001. Okay, so let me briefly go through segmentation by weighted aggregation. For lack of time, I can't go through it in much detail. But the basic idea is, talking about it algorithmically, you have your pixels on your graph, pixel level. Each pixel has its statistics, SU, SV, and there's an affinity between them. Okay, the first step in the algorithm is to build your first layer, going from graph G0 to G1. You do that by selecting a set of nodes to define that layer. These nodes need to satisfy what's called a strongly connected condition. That means that they have really high affinity to all of their neighbors, basically. Okay, one can do this with a formal optimization problem or a feed-forward greedy algorithm. Generally, when we do it with a single greedy algorithm for speed, but there are other ways to solve it with more mathematical principles. Okay. You have your graphs at the first level, G sub G1, and these form your nodes. And then you essentially need to push up the data and approximate it at that Corso level. You do this by essentially computing what are called interpolation weights that are average affinities from each of these nodes here to their superior nodes. So every node here at the finer level is connected to more than one node at the super level, and every node here is connected to every single node at the bottom level. So you can almost think of these nodes at the coarse level as like kernel functions over the whole entire finite level. Okay. Once we have these interpolation weights, we can accumulate statistics. This is where it gets interesting. So now, not only do we have intensities, for example, that are the mean intensity over all of the final level voxels that are defined at this lower level, but we can also accumulate histograms, variances, and so on. And this is where the method really gets powerful. Okay, so then you can define an affinity by just pushing up using those same interpolation weights to the higher level, and also incorporate and modulate that finer affinity with a coarser affinity, saying, well, we want to incorporate multi-scale information. We do that by taking the product of the two. If you don't do that, actually, if you're implementing this type of algorithm, you don't modulate it by an affinity function on the coarser level of statistics, the method essentially becomes the same as normalized cuts. But if you do incorporate these higher level statistics, and you repeat the process into a chain or into multiple layers, you get some really nice results. Right? So it's really able to find important structures in the image. So take this image here. This is a T1 scan of a patient. This is the same patient but a T2 scan. So T2 is more sensitive to water, so it gets a swelling in the brain, which is this whiter stuff here. Whereas the T1 scan will focus on the blood, right, in the tumor. You can notice as you walk up the hierarchy, the multiple layers in the hierarchy, that, for example, the enhancement on the side of the tumor is actually popping out pretty easily in here. And then you have the necrotic regions here. Finally, you also get the whole edema here, and so on. So some nice results. But this is just a feed-forward bottom-up algorithm. No classes, no learning, no data, no classrooms, anything like that. Okay? You can get we've tried a variety of different situations. You can get things like the caudate, the ventricle. These are subcortical structures of the brain that we want to study to understand how the brain functions. Okay, it's a powerful algorithm, works pretty fast, code's available. One problem: there's no classification. We haven't solved the recognition side of it. Another problem: it's a hierarchy. Which level of the hierarchy do you look at? It's like fundamental problems with SWA. Okay, and so we've proposed a method of overcoming those problems by taking a probabilistic view of the infinity function. Okay, so let's define a binary random variable x uv on each of the edges of the graph. Right, so this variable will take the value 1 if u and v should be in the same region, and it will take the value 0 if they shouldn't be in the same region. Let's just simply assume that we can say probability of x uv equal 1 is directly equal to the previously defined affinity function, e to the minus distance, blah, blah, blah. Okay? So if you have your conventional affinity function, you have just a simple black box generic measurement defined on some parameters theta. Right? So this doesn't let you say, well, I mentioned in the teacher channel, it enhances on water, so the edema gets picked up in the teacher channel. It doesn't let you learn affinity functions. Okay, but instead, if you take a Bayesian view of the affinity function and incorporate different classes at those C, U, and CV variables that each of the nodes can take, you're able to tune your affinity functions based on what you think the different nodes might be. Okay, so we're going to have a set of different affinity functions multiplexed pairwise over the different classes that we have. So we'll have one way of computing affinity if we think node U is brain and node V is brain. We'll have another way of computing if we think node U is brain and node V is tumor, and so on. And we'll learn these from data. Okay, so this will let us tune specific affinities. Okay, if you look at the mathematics behind it, it's essentially computing the affinity marginal by marginalizing over the possible class labels in the quadratic that nodes U and nodes V can take. After some algebra, you basically get a model-specific affinity function that's conditioned not only on the features at U and V, but also on the class labels at U and V, modulated by the node likelihoods, and then by some class prior. For example, brain tumor can never appear right near the skull, for example. It always has to be surrounded by some brain or something like that. You can incorporate some prior right there. Okay. There are two key enhancements that this Bayesian SWA makes upon the original rise to SWA. One of them is this way of computing affinity that incorporates a data-driven, or one can have an affinity classifier now, but essentially the parameters now are conditioned on the possible classes that the two nodes that you're computing can take. And if you think about this like the multi-layer case, so at low levels in the hierarchy, in the SWA hierarchy, there's not really much evidence, so those node likelihoods will probably be pretty uniform. But as you get higher up in the hierarchy, you're going to get stronger evidence that, say, node U is a tumor node, so that affinity function is going to have more importance. Okay? But the second key enhancement is that as we're doing this Bayesian affinity marginal, we're also computing a recognition or a classification of each node in the hierarchy. So with each node, we can associate a most likely class by taking the max likelihood over all possible classes. Okay, and this lets us do nice things like, for example, tag each region of the hierarchy as a tumor tag or an edema node, and so on. Even with very simple methods. So most of our work here is just based on the simple affinity function, weighted L1 distance, and our classification is just a Gaussian mixture model, independent over each channel. Okay, but you can see the improvements already in examples like this. So this is another example of a brain tumor where the tumor itself, or the edema, has encroached into the C-section in the center of the brain, even crossed the midline. And the original SWA is not able to capture that edema, but if you use the Bayesian SWA where you learn from the classes, you're able to see that the tumor is able to go, the classification region is able to get across the midline. Okay. And if you look at more classifications against human labels, against manual expert radiologists doing the labels, the second row here is just a max likelihood at each classifier, each pixel. Original SWA, Bayesian SWA. Largely, these two lower levels are similar, but it's only in the details, I guess you might say, of the regions that you get to see the quite differences. Things like this guy here. So this is a good example, slice 10. So these are all, every cone is a slice from the same 3D brain. Okay, so comparing these two scans here, you can see the benefit. Quantitatively, that's not that important, but it's about a 20% improvement in precision recall over the original SWA. Okay, so that's the first of the two layered methods that we looked at. This is more of a kind of joint segmentation recognition directly. And the second of the two problems is one that is a little different and one I think more closer to everyone in this room's personal nature, or so, because we're engineering scientists, computer scientists, whatever you want to say. We sit down a lot, right? sooner or later you're going to have a back problem. It's pretty well accepted, so and when you do, you can read my paper and you can find out why. Okay? So generally, there's something on the order of, I think 5 to 10% of Americans have a back problem at one time or another in their life, or at any given time. So you can have back problems like, so this is a normal disc, so I don't know how much you know about the spine, but basically you have a lot of bones and a lot of shock absorbers. Okay? What hurts are when the shock absorbers break and your bones rub, where the bones hit the nerve, the spinal column, right? So that's bad. Okay? So you can get things like degenerated discs, where the shock absorber is basically losing its fluid. The disc might bulge out of its region. It might actually herniate and push against the spine, the nerve bundle, or it might be shrinking, and so on. So this work, a radiologist came to us and said, the first thing we need to do before we can do any sort of pathology or CAD is find the discs. And I thought about it first, immediately, and I said, that's an easy problem, right? They're white discs, and there's only 6 of them in the lumbar region. This should be trivial. Okay? And then you realize it's not that easy when you look at the variation in things like appearance, both in one scan and across different patients, in shape, in location, in absence. A disc might be missing, there are size problems, and so on. So it turns out this is actually quite a challenging problem. Well, what we tried first was your basic off-the-shelf Markov random field model, right? So pixel-level features, right? So let's define more rigorously, right? So you have one graph I. These are the voxels of the pixels in the image you're getting. So we just use 1 T2, 2D T2s per image. You get the intensity level at this pixel. At the second level here, these are the hidden variables you want to infer. Level T. These will take things like from one of 7 possible categories. One would be not a disk. The other 6 categories are one of those 6 disks. Structure model at the D level. It's a chain graph where we actually have one. We know the size of the graph, the topology of the graph. Okay, and each of those nodes in D is connected fully to every node in L. So L are conditionally independent given D. And now we can infer directly appearance, just likelihood. What's the likelihood that each pixel is a disk? And we'll get hits on the spine as well, on the nerve bundle as well, but that won't matter because we'll be able to not only use pixel level features, but because we can model D variables as well, we can incorporate things like shape and geometric context. Okay, that's the basic benefit we're getting here. Okay, so ultimately we're looking to solve for D, and we'll define a model maximizing argmax over D, but we'll marginalize over all possible values, all possible mid-level random fields L. Okay, because there's no connectivity here, that will ultimately become a fairly simple maximization problem. But if you look after some algebra and some manipulation, you have again 3 terms. One of them is the simple appearance term, which is just your likelihood on whether or not this pixel looks like a disk pixel or not. Essentially, it's a Gaussian model on the intensity. But then you have some rich features that you couldn't do at the pixel level alone. You can actually do shape models, right? So disks are elliptical. Incorporate that. And then you can also have your location and context. So you can have the general rotation of the spine should follow an angle, and they should be roughly equivalently spaced apart, and so on. Right? There's no time to go through the rigorous math of the Gibbs distribution that specifies that 2-layer model. But ultimately, we need to solve it with an EM algorithm because of the missing data at that L level. We use generalized EM. And at each step, just want to note that inference is going to be fast and easy because we can factor that L level inference into independent local terms because there's no connectivity between the 2 nodes in the graph. Okay, and you kind of get, when you're computing the expected log likelihood, just a product over each value independently. This is quite easily and quickly solved. Okay, quickly, we can solve, so we get roughly 90% accuracy for training and testing, so the transfer is strong in the case of many abnormalities. So our training set has 20 normal cases and 80 abnormal cases. In this experiment 2, it's all abnormal cases. So we're able to deal with the abnormalities, but we do have some failure modes. Mostly this is when the L level inference fails completely, so it's too dark to get that. We're on average about 4 millimeters distance from the human labeled mean, and if you think about the size of a disc, I think it's about 3 to 4 centimeters, and 4 millimeters is quite minimal. Good enough for the radiologist. Okay, so I went through this talk fast, but I hope I gave you at least a brief understanding of what I mean by some aspects of layered models and methods. These are 2 of 5, 6, or 7 different methods that we're talking about in layered methods. We've applied the same method as the lumbar case to finding and estimating the geometry of building facades on a mobile robot while moving through an environment. We've applied the SWA algorithm and other graph-based hierarchical methods to video segmentation. And we also have one method which is not a model but more of an inference algorithm called graph shifts. And the basic idea is when you're looking at layered models, you can incorporate multi-scale information, minimize your computation, and incorporate more of your prior modeling knowledge into the problem. Okay, what we're doing now, I guess, is directly, as I'm saying, using Bayesian to evaluate other problems like video for defense and video understanding problems and so on. And I'm personally working on a sort of more formal framework of layered models. I'm happy to thank the NSFGA for funding this work. Thank you for listening. Any questions? Well, before I answer the question, so there's a demo at lunch which shows a lot of these videos, basically. If you want to see how it varies and so on, it's streaming hierarchical video segmentation. It's not real time yet, but you can see at the different levels, you can get things like deviceable videos popping up pretty regularly. And we're working heavily on this problem now.
I guess my question was about real time.
It's not real time, but it's
How far is it?
Chenling, how far is it from real time? I think it's a factor of 20 right now. Factor of 20. But we haven't made any emphasis on it. It is all in C code, so we're looking to improve the data structure and so on. So, but the code will be available end of June. So we released something called libSBX a few months ago now that has everything but the streaming method. And streaming method.
In your first technique, what kind of connectedness do you have between the boxes?
So in the raw voxel chain, it's a 6 connectivity. Up, down, left, right, forward, backward.
Okay.
But as you go, so it's it's called algebraic multigrid. So essentially, the connectivity at the higher levels is induced by the affinities that are affiliated up to you. So it's P, U, U variables, P, U, V, and so on. So the connectivity is essentially it's densely connected at the next level up, but you can prune away connections if there's no high level affinity. So you get these really interesting graph structures at the higher level. Yeah, but that all comes naturally right out of the algebraic multigrid.
You guys can apply that to other areas of the body besides the brain.
So we've applied it we've applied it to video as well. So the problem is that the limitation of that method is that it's extremely memory intense. So I mentioned that every course level node has a full connectivity to every final level node. I mean, that's basically a whole video, right? So we're a whole data set. So for every course level node, you're storing a whole data set around it. You can't do that in a challenge. And that's basically been a computational limitation.
Thank you. Speaker again.